So our speaker today is Cole Miller, professor from the University of Maryland in College Park. He actually is really a genius. When you started college at 12 or so, that kind of tells you. He finished his master's and PhD degree at California Institute of Technology, getting a PhD on the Finney in 1990. He had several postdoc positions at the University of Illinois at Urbana-Champaign from 1990 to 1993. He was briefly a visiting scientist in Ardita in 93, and then became research scientist between 1993 and 1999 at the University of Chicago. He joined the faculty of the University of Maryland in 1999, where he remains since then. He was a chair of the Maryland Astronomy Center for Theory and Computation, twice actually, between 2004 and 2006, and then between 2017 and 2019. He is a Redwood Excellence Professor at the Redwood University in Yemen, Netherlands. And with that, I'll give the microphone to Cole, and you may start.
Thank you very much, Igor, and thank you everyone for showing up at these, as usual, unusual times, but I hope we can all bond together in our appreciation for neutron stars. I am indeed going to talk about some of the recent work done using NASA's Neutron Star Interior Composition Explorer mission. This down on the left here is an artist's conception of what it would look like on the space station. And the bottom right are the actual heroes of the story, because it's easy as a theorist or a data analyst to become entranced with our own work and forget that the people who build the instrument are the ones who make everything possible. Fairly simple outline here, although I presume that you are with me in believing that neutron stars are important. I wanted to emphasize why neutron star radii, if measured not just with precision, but also with good accuracy, are especially important. And then I'll tell you about the measurements of the mass and the radius of this particular pulsar, which we announced in the Astrophysical Journal letters last December. There were two groups that did this work independently. I led one, and the other was led by Anna Watts at the University of Amsterdam. And I'm going to talk only about our work, but I do recommend that you also read their papers in the App Data Letters Focus issue from last December. The main thing that I want to get across about the two groups is that although we did our work independently, wrote codes independently, and so on, the favored models from the two groups are completely consistent with each other in not just the mass and the radius, but also to a remarkable extent in the spot patterns. This is not necessarily a guarantee. And yes, it could be that we're both equally wrong, but this gives us some degree of confidence. As Igor said, please feel free to ask questions at any time. I've tried to set this up so that were I uninterrupted, it would only be about 40 or so minutes. So I hope there's a lot of time for discussion. Also, I am going to pause 2 separate times during the talk to see whether anyone would like to pursue some special discussion points. Now, with this in mind, I believe that the audience today is mostly nuclear physicists. I am an astrophysicist. And to me, a lot of nuclear physics is a bit of a black box. I try to educate myself a bit, but if one of you told me that you had a new model of neutron stars involving tachyons, I would probably say, oh, gee, that's cool, and not really be in a great position to judge it. It's possible that for many of you, the opposite holds for astrophysics. If somebody goes up and says, hey, I've measured a neutron star, this is the radius, then you may say, great, let's put that radius in my models and see what comes out. One of the things that I'm hoping to do today is to open up that black box at least a little bit, to tell you a few of the concerns we have, some of the things we're doing to address those concerns, and to give you an opportunity to ask burning questions about any issues that you might have or how we might go forward. But first, since I don't want to tease you, and assuming you haven't read our papers, for this particular pulsar, about 200 hertz, it is an isolated pulsar. This is important because it means that we do not have independent measurement of the mass of the pulsar. We have to get both the radius and the mass independently directly from the NICER data. There are other pulsars we're observing where we do have binaries, and therefore we can get estimates of the mass, but this one seemed especially free of any particular systematic issues. We are working on others as well, of course. The equatorial radius, roughly 13 plus or minus 1 kilometers. Gravitational mass, a quasi-standard, roughly 1.4 plus or minus 10%. Now, in our work, we looked at 2-spot configurations and 3-spot configurations, and very slightly in a Bayesian evidence sense, the 3-spot configuration is favored, but not by a statistically significant amount. So they're almost equally good. Remarkably and surprisingly, all of the spots, whether it's 2 or 3, are in the rotational hemisphere opposite the observer, and at least one spot is highly elongated. This is already an indication that we're learning things, because after all, if you look at a textbook, you see a nicely centered dipole with spherical or maybe possibly annular spots. So these are things that we're starting to learn. Now, radii. I may not even need to make this pitch to you. However, the point is that we have measurements of various aspects of neutron stars, including, as I'm emphasizing in this figure, we have some measurements of fairly high mass pulsars. This particular one has a mass a little over 1.9 solar masses, and there are ones up to about 2.1. And that's important. It ruled out a lot of proposed equations of state that had previously been viable. But as you can see from this particular figure, if you could learn one thing about a neutron star to high precision, what would it be? And many nuclear physicists I've talked to have suggested that they would like to know the radius very precisely. However, in contrast to the mass, which in the right circumstance could be measured with very good precision and high reliability, the radius is a different story. Something that I'll emphasize in just a bit here is that there are a lot of measurements that have existed over the past many years, which, if the assumptions in modeling are correct, give us quite precise radii, few percent in some cases. However, the problem is that we don't know. The assumptions could be quite wrong, and we wouldn't know about it. This means that even if you have a formal statistical uncertainty of 5% in the radius, you can in some cases have a 50% error in your actual measurement because of systematics. And this is a case where, as I'll again emphasize, the particular modeling of NICER data can help a great degree. And again, to not tease you here, this is what we have so far, this little error ellipse. This is what we have at the 1 sigma, or 68% total confidence, from the measurement of this particular pulsar. And maybe you look at this and you say, well, you know, I was hoping for something better. It spans a whole lot, which, okay, although you're still doing slightly better if you're in the middle. So this is an advance. Also, this is just our first attempt. By the end of the NICER mission, we're going to have more than twice as much data as we currently do on this pulsar, and we will have other measurements as well. There are therefore real prospects for us to be able to understand better the equation of state, if not necessarily the composition, of very dense matter. Now, I promised a discussion of why it is that radius measurement is tougher than you might think. And if I were to start off here, I would say, let's first of all imagine how we would measure the radius of a star like the sun, but not the sun, at a normal astronomical distance. And so far, we can't resolve it in an angular sense, and therefore, if we wanted to measure the radius, we'd have to use a different method. And the method that actually seems to work pretty well is you treat the spectrum as if it's basically a black body. You figure out the distance, maybe by parallax or some other method. You get the flux, you measure the temperature of the black body, you use your black body formula, voila, a radius. And when you use that method in cases where you can check it, like with the actual sun or Betelgeuse or things you can analyze using astroseismology, that method works pretty well for sun-like stars. Do the same thing with a neutron star. It looks like a Planck spectrum. Do your measurements, and you get ludicrous answers, like 2 kilometer radii. So you know that can't be right. You need to work on better spectra, but most of the analyses of X-rays prior to NICER essentially looked at flux and spectrum with a couple of other things thrown in on occasion. Effectively, what you would do is you would assume that the star radiates uniformly with the same effective temperature over its entire surface. What I have here on this slide is an example of how that can go terribly wrong. What I've done is I've generated synthetic data using locally black body emission and isotropic, where the temperature varies smoothly from KT of 2 keV, or about 2 times 10 to the 7 Kelvin, to about 1/10 of that at the pole, so a wide range. But I'm modeling this as if the temperature is uniform over the whole surface. Now, the first thing to notice in this plot, where, by the way, the number of photons is quite competitive with X-ray bursts or other measurements, there's no evidence of something wrong. Chi-square per degree of freedom is fine. There's no red flag here. The fact that it's a little above 173, not a big deal. There's no indication that you're using the wrong model. As it happens, the radius I actually used to generate the synthetic data was 12 kilometers, but using a fit with a single temperature across the whole surface, not only do I get the answer wrong, I get it very confidently wrong and very far off by about 10 standard deviations. This is actually fairly typical. If you have a temperature variation over the surface, assuming a constant temperature gives you an underestimate for the radius. And you could even get larger corrections. This is something that is at least a potential issue with the majority of the measurements, especially involving X-rays, prior to NICER, meaning that you could be very wrong, but you would not know it. And that's a bad combination. This has therefore been an extreme focus of the work, especially that I have done with Fred Lamb of the University of Illinois and our collaborators. And what we have found is that in contrast to that other type of data where you're essentially looking at a spectrum integrated over many rotational phases, here with NICER doing X-ray observations, we're looking at rotating neutron stars with hot regions on them, hot spots, if you will. This gives you not just spectral information, but also information about the phase of arrival of each photon. This is a huge extra amount of information. And in our work, we've done a lot of analysis of synthetic data of the NICER type, where we have looked for what will happen if we assume one thing about a spot and do another thing with the modeling. For example, maybe we assume, and when we generate the data, that the spot is an oval, but we model it like a circle. And what we have found in all of the cases we've examined is that if there is a statistically good fit, for example, in the chi-square sense, then there's no significant bias. And it's because of this extra information. This is the key factor that gives us, of course, cautious optimism that the answers we're getting with the NICER analysis are not just relatively precise and will get better, but are also reliable. So here's your idea in brief. This, by the way, is from the NASA press release on the papers. And no, we don't expect that there's all this kind of fine structure. This just kind of looks better. Here we're imagining 3 hot spots. So we have 1, 2, and 3 in this particular case. And as it rotates, then we have the radiation coming from the spots, which is Doppler shifted and gravitationally redshifted and whatnot. And essentially what we do is Bayesian fits. We trace rays from these hot spots to us. We can assume in a particular parameter examination that we have a given mass, a radius, observer inclination, all these things. We basically compare that with the data and then do the usual Bayesian thing. We iterate to get best values and uncertainties in all of our parameters, the most interesting of which are the mass and the radius. But I promised that I'd try to open the black box a little bit. Maybe you just trust us, and if so, that's great, I appreciate that. But you can start asking some questions once you start looking at the details. In particular, we are fundamentally tracing photons from the star to the observer, us. If the star were not rotating, this would be really simple. Because of the spherical symmetry of the external spacetime, This means that a given photon travels in the vacuum between the star and us in a plane. As a result, all we have to do is figure out the angle it travels, and we can determine the path. We don't have to actually trace the path step by step from the star to the observer or the reverse. However, when an object rotates, it drags space-time with it. This means that you no longer have spherical symmetry. You have axis symmetry, but this means that unless you happen to be along the right plane, you're going to have a twist to the orbit. So as a result, in principle, you'd actually have to step through and trace the entire path. That takes a lot longer than just asking what angle you need. In addition, a rotating star is oblate. What is it then that we can do about this? One thing that is tremendously useful to us in terms of the speed of our codes, I mentioned frame dragging, but it turns out not to matter at the 200 hertz or 400 hertz, which are the stars that we're examining using NICER. What do I mean by doesn't matter? Well, here's an example that is in one of the support papers that we had in last December. We have different approximations. For example, the Schwarzschild plus Doppler approximation is one that Fred Lamb and I introduced, where we pretend that despite the rotation, the star is spherical and the external space-time is Schwarzschild. But you do the other things correctly, like you put in the right special relativistic effects. And that's something that, when compared with a full numerical analysis solving everything self-consistently, does fairly well. In this particular case, we're talking about a 1.5% difference at the most. However, an almost equally fast approximation introduced by Sharon Morsink and her colleagues is the so-called oblate Schwarzschild. And this is something that at first you might imagine is a self-inconsistent approximation. What you do is you take a reasonable analytic approximation to how oblate the star will be at a given rotation rate, mass, and radius. But then you treat the external space-time as Schwarzschild, meaning spherical, so no twisting of the ray paths. And you do the special relativity correct as well. And this, you end up with something that is tremendously accurate, far better than anything we're going to get using the statistical precision of the NICER data. And I say this may seem self-inconsistent because there are arguments in the literature more or less as follows. When you start rotating a star, frame dragging comes in at first order in the rotation. Oblateness comes in at second order of the rotation. If all you're doing is counting orders, you'd think you must include frame dragging if you include oblateness. But no, in fact, there seems to be the effect that the main thing of frame dragging is it shifts the image rather than distorting it. And there's a coefficient to worry about as well. This means you can actually ignore frame dragging. You have the benefits of the spherical space-time, and this speeds up the code dramatically because we have to do some tens or even hundreds of millions of ray paths that we're checking in order to do our full calculations. So this is a good thing. The other aspect about rotation is that it changes the relation between mass and radius. The typical thing that we all plot is the mass versus the radius for a given equation of state for a non-rotating star. However, it's rotating, so there's a difference between the equatorial and the polar radius. There's also a difference a little bit in the maximum mass you can get. However, a figure from our paper, calculated by Sharon Morsink again, is that if you look at the difference between a non-rotating star and one which is comparable to what we're looking at for J0030, the pulsar, it's negligible compared again to the statistical uncertainties we get from the analysis. This saves us a whole lot of pain and effort. What are the models used in FITS? And here again, trying to pry open the black box a little bit. I'm just laying out what we're doing, and then I want to question them and then explain why I think it's okay. First, we consider uniform temperature spots. These can have different temperatures. If they're different spots, they can be anywhere on the star. They can overlap in any way. They can be oval. We have unmodulated background and so on. But something you might be thinking about here is physically, first of all, you're getting these spots by the high Lorentz factor particles that are bouncing back and forth in field lines, part of the radio pulsar mechanism. So you slam into the surface, you deposit energy, the energy bubbles up. This is how we think we get hot spots. But the thing is, there is absolutely no way that the spots can actually have a fully uniform temperature. The idea that you would have a perfectly uniform temperature and then dropping to nothing is absurd. However, remember I said that Fred Lamb and I, along with our collaborators, have done a fair amount of work in which we generate synthetic data using one set of assumptions, and then we analyze it using a different standard set of assumptions. Among those, we looked at cases where we generated synthetic data where the spot had a variable temperature, but we fit it using a model where the spot had a uniform temperature. And the answer is no bias. Why is that? It's basically because there's a huge spreading out of the radiation from the star. The radiation from an individual point on the star is pretty broad. It's not isotropic, it's a little beam toward the normal, but it's still pretty broad. And then once that comes out, gravitational light deflection smears it out further. This is something that eliminates fine distinctions and means that these models appear to be actually good, not just in the statistical fit sense, but also in the sense of not producing significant systematic errors. One of the things we have to do, of course, is to demonstrate that when we generate synthetic data, we can recover it. This is a test of the whole pipeline. And this is an example from our paper. We generated things where the mass and radius are right here. And we did a couple of choices of the nicer data that we analyzed. And so this is at about 1.5 sigma. We've done a lot of other things, and it's in the 1 sigma as often as you would expect. This appears, therefore, that with, say, at least 2 ovals, we are capable of recovering what we put in, which is a minimum condition for us to be at all confident in what we might be learning from nicer data. Are there any questions at this stage?
Let's see, I don't see any raised hands.
Okay.
I have a question.
Go ahead.
Henry DeYoung here. Does the, can the rotation rate or the position of the spot affect the frame dragging results?
The rotation rate definitely does. For example, if you were to spin a neutron star up to its maximum value, maybe 1500 hertz, at that stage you would certainly not be able to ignore the effect of frame dragging. As far as the positions of the spots, perhaps what you have in mind is that if you have spots fairly close to the rotational pole, the frame dragging would be less important, near the equator more important, and that's true, but at any position on the surface for 200, 300, 400 hertz, it turns out not to be significant, meaning that the error that we make by ignoring frame dragging is considerably less than the statistical uncertainty from the data.
Thank you.
Sure.
Okay. Let's see, any other questions? Actually, I sort of had my own question. In one of the slides, you mentioned that the equatorial temperature might be around like 2 kiloelectron volts and 12.2 kiloelectron volts. That's fine by the numbers, but I was kind of confused. This is just for this star, or there is some systematic reason for having the pole temperature lower?
This was a complete hypothetical. The actual temperature I used in that case was supposed to model more what you would have from a thermonuclear X-ray burst. The stars we're looking at are not accreting. The spots are entirely more from the radio pulsar mechanism. The lack of accretion is an important simplification, so we focused on those. The temperatures in that case are more like 10 to the 6 Kelvin, so closer to 0.1 keV in energy than 2 keV. So that was a different state, just to prove that if you make the assumption of uniform temperature, you can be wrong and not know it.
Right. Well, associated with that, the reason is this that I asked. When you have an isolated star, I would guess that the temperature should be higher on the sports, which might be coinciding with the magnetic pole. Mm-hmm. Wouldn't that be the case?
Yes, that's a general assumption. But it's not like, it's not going to be 2 keV. The temperatures are going to be a lot lower because you don't have active accretion going on.
Right. but I'm just trying to think theoretically where those spots would be and what could be a potential physical explanation. And yes, magnetic field perhaps would be one of them.
Yes, that's right. So the magnetic field is believed to be strong enough to, well, to produce these hot spots, but not strong enough to significantly affect the radiative transport at the X-ray energies that is the focus of NICER.
Right. Any other questions from the audience? I don't see any raised hands or chat messages. So unless we get another question within a second or two, I think you may proceed.
Okay. Thanks very much. Here are the results that we have. We have looked at two different models, one with 2 ovals, one with 3 ovals. Remember that the 3 oval model is formally, slightly, but not statistically significantly preferred to the 2 oval, but they give basically the same results. And this is good because we have independent analyses of these two, and you could always imagine that there would be different, comparably good fits, and you could worry about the possibility that they would give you different mass radius posteriors. But as it is, here you are. This is the inner 68% region. This is the outer 95% region, so kind of 1 and 2 sigma. And this is the concentration. So we're talking about things that are 13 plus or minus 1 kilometers, more or less. And in fact, if we look a little bit more closely at this, we can do one-dimensional posteriors, marginalizing therefore to get to the mass, the radius, and the distance. And the top is for the 2 oval model, the bottom is for the 3 oval model. Again, very comparable. This here, this distance, the dotted Gaussian is the prior. So we don't really learn a lot about the distance from the NICER data. However, this has turned out to be kind of an important check because NICER data in their energy channels goes down to lower values, but at least with the instrument response that we were using at the time, if we go to too low a channel number, then we start getting what appear to be significant biases. So the posterior would be pushed to higher distances. But channel 40 and above with that response seems to be just fine. Here we have the bolometric waveforms, where the dotted lines are the individual spots. As usual, here we're looking over 2 cycles so that we can see all possible patterns. And here we have the 3 oval fit. And again, this is very similar. We end up in the 3 oval fit with, as you'll see, a spot that is fairly close to the opposite rotation pole, but it contributes at least a little bit. Here now we have an actual comparison with the data. There are different comparisons we can examine. In this case, we're looking at the bolometric residuals. Now, let me explain why we're doing this. As I mentioned, our analysis is a Bayesian analysis. We're doing Bayesian parameter estimation. When we look at different models, we're doing Bayesian model comparison. For those of you who have worked with Bayesian statistics, you know that a big advantage of it is that it allows you to feel morally superior because you're doing things correctly. However, like other morally correct things, it can be a lot more work than doing it the easy way. However, I'm not a fundamentalist Bayesian. And one thing, as you know, that is lacking in Bayesian analysis is any kind of measure whatsoever about whether you have a fit that is good in an absolute sense. So what do you do about that? Well, one thing you can do is you can briefly slide off the Bayesian wagon, and you can use a bit of frequentist statistics, in other words, chi-square. You can calculate the chi-square per degree of freedom and see how that stacks up. And doing it this way, that's what we're looking here, chi, so this is the signed square root of chi-square. And we see that there are no major excursions, and in fact, the overall chi-square is pretty good. We can even look at the phase channel data. This, rather than integrating over all of the channels, we're showing the whole thing, or here's chi, -3 to 3 sigma. There's no pattern here. This is something that is reminiscent perhaps of some test patterns back in the old days of TV. But what we find is that with this substantial amount of data, the chi-square and degree of freedom are as given here, which you would expect from a correct model 12% of the time. That's pretty good. This is a huge amount of data. What this tells us is that there's no obvious red flag about the fit. There's nothing seriously problematic about it. We're not getting distances far larger than we know the distance to be. We're not getting a fit that is miserable by this model. It does not, of course, prove that we have the right fit, but it is something that we can use to give ourselves a little bit more confidence. The spot patterns are rather unexpected. Top is the 2 oval fit, bottom is the 3 oval fit. On the left here, we have an equal area projection over the whole sky. On the right, we have what we would have seen from the opposite rotational pole from the hemisphere we're in. The bar represents the observer inclination, so that's our inclination. And what we notice is that not only are these things all in the southern hemisphere, the opposite hemisphere, but they're not circles. This one is quite definitely a large arc. And this one actually, it turns out that even its parameters are well away from a circular pattern. So this is already telling us that there are things we have to consider in more depth about the nature of the magnetic fields and exactly what we expect for these stars. Indeed, this is a case where we can turn to planetary science for another example. We always try to think about center dipoles because that's the simplest thing, that's what we start with, and wouldn't it be great if we had that? But we know when we're able to look at it very closely that this is not always the case. Here we have Uranus and Neptune, here are their magnetic fields, and these are very definitely not center dipoles. And in fact, in retrospect, we really shouldn't have expected anything as simple as a center dipole. You think about these rapidly rotating pulsars, and the idea is that they started out normal, whatever that means, and they underwent a lot of accretion, somehow reducing the magnetic dipole moment by orders of magnitude, spinning down initially, spinning up later. Really, there's no reasonable expectation that the spots have to be simple. So this is perhaps not a shock. Are there any questions at this stage?
Any questions?
So I have a question.
Go ahead.
Can the spots be any distance above the surface?
Yeah, it's an interesting question. The physical model we have of how the energy is deposited is that you have, these are active radial pulsars, and that as part of that process, you have electrons and positrons mainly with Lorentz factors maybe 10 to the 7 that are going back and forth and hitting. They're accelerated along the field lines by the E parallel to B, then they hit the surface. And when they hit the surface, they deposit energy. These are cool enough neutron stars that there should effectively be no atmosphere. And when people have done plasma physics calculations, they have found that the energy should be deposited quite deep in the star compared to the number of optical depths. So it's many optical depths deep. The energy being generated high is unlikely, and it should be deep enough that it can bubble up and give us a characteristic pattern. There is one thing that we checked, however, because we were also worried about precisely what you were thinking. We were wondering about at least possible contamination by some other X-ray emission, like a power law type of emission that might happen, indeed, well above the surface. And we can look at the data, and what we find is that this is unlikely to contribute anything significant at the energies which are the focus of our analysis. They can dominate at 5 or 10 keV, but not more in the tenths of a keV to a couple keV that seems to be the dominant part of this information.
Okay. Any other questions? I don't think anybody indicating any questions, so let's go then.
Okay, in that case, well, thank you for withstanding the astrophysics. And now we'll go for a little bit of the nuclear physics payoff. We can ask ourselves, what is the contribution that NICER has made to our understanding of the equation of state. And there are different ways of phrasing this, of course. One thing we can set up is that we do, of course, know something about the equation of state. The standard thing to do is to assume that we know it perfectly up to some moderately low density. We assume half of nuclear density. And so we can use something like the QHC-19 equation of state up to there, and then parameterize it beyond that. There are different parameterizations. Here we're looking at the one that was introduced by Lee Lindblom and is being used extensively by the LIGO team for analysis of gravitational wave data. What we're looking at here is going from nuclear saturation density to twice that, focusing in there. And this is the ratio between the 5th and 95th percentile of the pressure at each density after the nicer data have been included to before. And before includes the knowledge that we have several massive pulsars, the upper limits on the gravitational wave, from gravitational waves of the tidal deformability and so on. So all of that has already been put into this, and now this is the improvement. And this is moderate, helpful, you'll probably take it. And something to remember is that this is the tip. We're going to do better. We're going to double the exposure time, certainly by the end of the mission, if not necessarily by the end of this year. We're going to have other pulsars as well. And all of this is something that can be brought together in frameworks. We've thrown our hat into the ring, working with Cecilia Cadenci and Fred Lamb. We talk about what we feel is an efficient way of including all of this information from gravitational waves, from NICER, from heavy pulsars, from laboratory measurements if necessary. I think, therefore, this is encouraging. So this was kind of the short version, but now let me go into some more detail and show you one of the payoff figures of our paper from 2019. What we're looking at here is two different rows that have different parameterizations of the high density equation of state. The top one is what I just showed you, this Lindblom spectral equation of state. The bottom is a piecewise polytrope with a number of segments. We'll focus therefore on the top one because it's more or less the same as the bottom. By assumption, down here at the left end, we know the pressure because we've taken our equation of state up to half nuclear. Now in the left panel, we show for each of these number densities, and this is now log, the 0% to 100% range and 5% to 95% range. Moving on to the middle, the dotted line was the 5 to 95% range previously, and now we add in information from NICER. That's this band here, so now we've restricted the 5 to 95% range rather substantially. If we then add all the other information from heavy pulsars and gravitational waves, then this dashed line was the 95% using NICER, 5 to 95, and the solid line is now what we have when we include everything else. These three dashed lines are the soft, medium, and hard equations of state from Hebler et al., just as characteristics. Something that I think is really quite encouraging is that whereas the initial, that is to say the priors, were very different between these different parameterizations, by the time we're adding in all this information together, we're really starting to converge. And we expect that to be much more so as we add data and add additional pulsars. I think this is therefore a very encouraging sign going forward. So in conclusion, the first measurements that we have for this pulsar from NICER have already tightened equation of state constraints in a significant way. And so that you can play with this as much as you want, at this URL, Zenodo, and this is also mentioned in our paper, we have the full posterior samples over all parameters, and separately, to make it easier for you, the mass and radius samples. Therefore, you can plug this into whatever mechanism you have and play with it as you wish. To emphasize again, something I really stressed near the beginning of this talk, the key, in our opinion, is that the measurements appear reliable as well as precise. Previous measurements, could have been right, but you can't really tell because there are ways that systematics could completely shift the answer. So far, at least, that does not appear to be the case for the NICER measurements. And then, looking forward, we have a doubling or more of the data set for the pulsar I featured, and we're also going to have analysis of other pulsars, especially pulsar J0437, which has the highest count rate and therefore ultimately may give us the best precision, and J0740, which is the pulsar with the highest precisely and reliably measured mass. These should provide not just double checks, but with a higher mass pulsar, extra leverage, because in principle, you have components of the star which can get to significantly higher density than they would for a 1.4 solar mass star. We therefore expect that in the next couple of years, maybe even in the next 1 year, we should have significantly improved constraints. So in conclusion, I've liked neutron stars my entire research career. I did my PhD on them, and way back then in 1990, the assumption was that we would start getting tons of great information from spectral lines, and we'd learn all this stuff, and we'd learn about the equation of state. But nature has not been so willing to give up her secrets. I am therefore very pleased to note that I have apparently consumed enough vegetables in my life to survive long enough to see a data-rich era in the study of neutron star structure. Thank you.
Well, thank you. Thank you very much for a very nice presentation. Now let's see if we have any questions. So anybody from the audience, any questions? Either raise your hand or let me know in the chat message that you have questions. Okay, yes, go ahead. Veronica, go ahead, please. Veronica Dexheimer.
Sorry, trying to unmute myself.
Yeah.
I know that you guys are going to look at some interesting objects, for example, with larger mass. But besides that, are you going to look at interesting objects, for example, that rotate faster or have larger magnetic fields? What should we expect in the future?
J0740 has a rotation frequency of 346 hertz compared to this 245. So that is a higher rotation rate, there's no question. If you're thinking about things that might be 600 hertz or so, there's a limit, because even with millions of seconds in each source, there's a limited number of non-accreting pulsars that have a high enough X-ray flux that we can accumulate the necessary number of counts. So there's a limited number we can examine. In terms of stronger magnetic fields, the part of the issue there is that, well, when you have stronger magnetic fields, you rotate more slowly, and the rapid rotation is one of the things that gives us good information and breaks degeneracies. So that'd be a little tough. Also, the modeling, if you have magnetic fields strong enough to have an effect on the radiation transport, becomes much more complicated. The kind of tables we're using would have to be expanded by very large factors. So at the moment, we're thinking about a limited set which have rotation rates that are all fortunately small enough that we can use this oblate Schwarzschild approximation. So thanks for the question, Veronica.
Okay, next question is from Chuck Horowitz, please.
Nice talk, great talk. What might the next X-ray telescope to follow NICER look like? Seems like NICER has been a great success.
Yeah, I think it has. And I think to answer that, I want to mention why NICER has been so successful in this case. It has good area, it has extremely good timing of the photons, but at least as important as those things is that it has an observing strategy where the idea is that we look at a small number of neutron stars for a long time each. The results I'm showing you here came from about 1.8 million seconds on target. You can do that with a mission like NICER on the space station. It's a comparatively cheap mission for NASA standards. If you think about what you would want to do, well, of course, you'd want to increase the area a lot. You'd want to increase maybe the spectral precision and things like this. But the challenge I think that would really show up is if you had a really excellent instrument of that type, would the operators be willing to stare at things for a couple million seconds each? So it's not obvious. I think that for a while, NICER is going to be a big thing. If you look at brighter sources like thermonuclear X-ray bursts, then you don't have to wait as long to accumulate counts, and therefore excellent time resolution and large area would be good, but there may be some other complications as well. I think we'd like to hold on to NICER as long as we can because it's not obvious that a good successor will come up. If you can get polarization, that'll help as well, at least to some extent.
What limits NICER's mission?
Time. And the other thing which you would want to improve about NICER is its background. It has a fairly large field of view, and so a lot of things come in. So if you had duplicates, somewhat better shielding, and a little lower background, that would help a bit. But time is the main thing now.
How long will the mission run for, and can it be extended?
It was, last year, it was given a 3-year extension, and therefore in a couple of years, it'll be up again. And in principle, the NASA Senior Review, they'll look at it and decide whether they want to keep it going. And if they're now going to go on a 3-year cycle, because previously the NASA Senior Reviews were on 2-year cycles, having that extra 3 years would obviously be important. But I would say that the more interest shown in the results by the community, the more that the NICER PI and deputy PI are going to be able to make a case to NASA that they've got a good thing going.
Okay, any other questions? Yeah, we have several questions. So the first one is Henry de Jong. Yes,
hi. I have a question. With the data that you've been acquiring and or your experience, can you discuss the core of the neutron stars, structure and composition in general, especially with respect to the radius?
We cannot say anything about the composition. Formally, we can only say something about the equation of states that the pressure is a function of energy density. Back when I was young and naive, maybe 10 years ago, I imagined that nuclear physics was done from first principles and they wouldn't have to worry about phenomenological models. But I think what we have to do is hand the information to you guys and say, what do you make of it? That's primarily what we're going to get for now. If we're thinking more generally about how we might learn about neutron stars, something that has been brought up is that if you are able to confidently establish the surface temperature as a function of age of pulsars, especially ones with known masses, this will give you a very different slice through that might actually help you get at the composition a bit. But what we're doing is P of epsilon.
Okay.
Thank you.
Sure.
Next question from Pavel Danilevich.
I have a question about the hotspots. Are these hotspots plausible? What would be the physics behind them? And is there anything that can be learned from what you find about the hotspots?
Yes, there's actually a paper on the archive from other members of NASA and the NICER team, which I guess it appeared last week. And I think Kathalopoulos was the first author, and Alice Harding and Zeror Singh and so on like this. And the answer is yes, you can actually get things like this. One way is that you add additional multipolar components to the magnetic field. There's work done by Sam Gralla and his colleagues. They call it a quadradipolar field, which can also get you these sorts of patterns. I think, therefore, that this agreement between the two groups about the general structure of the spots is something that is allowing people to open their minds a little bit beyond the center dipole.
Thanks.
Okay, next question from Jamie Stafford.
Hi, thanks for the nice talk.
Thank you.
Very instructive. I have maybe a bit of a naive question. I'm coming more from the nuclear physics background, but do your constraints on the equation of state also put a constraint on the maximum mass of a neutron star, or is that totally different?
Oh, I'd say that's actually quite an important question. In principle, yes, they would, because anytime you are constraining the equation of state, then you're limiting the P of epsilon that might apply to neutron stars. And within that context, you can calculate the posterior probability density for anything you like, including the maximum mass. Now, as it happens, because we're getting things like, say, 13 kilometers as our best estimate with plus or minus 1 kilometer uncertainties, using just that, you would think that the maximum mass could be quite high, or it could be lower. So really right now, the maximum mass is mainly limited by the existence of some heavy neutron stars. That's limiting it from below. And there are arguments that are less robust, more susceptible to astrophysical whatnot, that are coming from the existence of short gamma ray bursts, and especially the gravitational wave double neutron star event. So those are things that are sandwiching the equation of state more strongly than just our measurements will.
Mm-hmm. So it's a convolution of many different things that contribute to that maximum mass then.
It is, yes. I mean, we're not quite at the level of cosmologists where we declare a concordance or something like that. But yeah, when you look at the gravitational wave results for tidal deformability, this would push things a little bit towards a softer equation of state. If you look at our results, that pushes it a little bit to harder equations of state. But they still play well with each other. There's a good intersection.
Okay, thank you very much.
Thank you.
Okay, any other questions? I had a question along the way, and I forgot to ask. Since you have very specific technique, I suppose it will be better used for certain objects and maybe less useful for other objects. Wouldn't it be better to concentrate on the pulsars that are spinning slower so that you get a better data, or that is not really important?
That's a good question. There are several things that play into which pulsars we would like. Obviously, we'd like pulsars that give us a lot of counts, that don't have a lot of things nearby them to contaminate the data, although we have techniques for dealing with that. In terms of the rotation rate, we are kind of already in the sweet spot of 200, 300, 400 hertz. If we're much larger than that, we would start worrying about deviations from the spherically symmetric nature of the space-time. If we're much less than that, then although we certainly would get information from occultation of the spots, the information we get from the Doppler shifts due to rotation would obviously be much less. So where we are is a reasonable place for us to do our analyses.
I see. So concerning the same sort of thing, in terms of the other parameters of the stars that may be important or useful for measuring more reliably, mass radius parameters, what are the other things?
Yeah, so one of the exciting aspects of now going forward to these other two pulsars, because they're both in binaries, this means that we have an independent and reasonably precise measurement of the mass. We have a reasonable measurement of the observer inclination relative to the orbital axis. It's a little technical point, not directly the rotation axis, but it is believed the evolution of the system is going to fairly closely align the two. So we kind of know the rotation axis inclination too. And the distance helps as well. All of these things we put in, we can bring in maybe other data sets as necessary. We're continuing to develop, but we have good tests of our current data analysis pipeline, which includes as much of this information as we can possibly put in.
I see. Wouldn't the accretion spoil the data in some way?
It would, however, just let me make clear, these are binaries, but these are not accreting binaries. The companion in each of these cases is a low mass star or a white dwarf, but any period at which it was actually flowing matter over to the neutron star is a long time in the past. And that means that in terms of the actual analysis, we don't have to worry about it. And that's a very good thing. In principle, accreting neutron stars have X-ray count rates, which are just overwhelming. You'd love to be able to take the data. But the problem is not only do you have to worry about exactly how the matter is funneled down into the star, but the accretion brings with it plasma, and the plasma produces a bit of a fog around the star. And this does things like change the relative amplitudes of harmonics of the rotation in the pulse waveform. And that makes it much more difficult to analyze. So we are definitely focusing on ones that are not accreting.
Okay. Chuck has another question.
Yeah, thanks. What have we learned about neutron star atmospheres?
One of the things,
Can we get more reliable radius estimates just from looking at fluxes from other systems?
So that's, yeah, this is a good question. And this actually comes down to, in some sense, quality of data in the following sense. I mentioned early on the concern about using just fluxes, spectra, distances. And one of the big issues of our potential concern with systematics is that there are some of these neutron stars, the so-called quiescent low-mass X-ray binaries, where formally, if you use a hydrogen atmosphere, you get a good fit. If you use a helium atmosphere, you get a good fit, but they're 50% difference in radius. Well, that's a problem. They're equally good fits. You cannot tell the difference. You may have a feeling that it should be hydrogen in some cases, but maybe it should be helium. You have a very low count rate and you're not staring at these things for millions of seconds. In our case, for this particular pulsar, our primary analysis was done with hydrogen. The reason is that the surface gravity is so enormous that extrapolating formulae from 40 years ago, you would expect the lightest element present to rise to the top within seconds. That's probably hydrogen. However, we also have helium tables, and we've done those fits, and these get values of parameters that are unreasonable, like masses approaching 3 solar masses would be the best guess. And the fit also isn't quite as good. This is something we'll keep alert to, because there is a case where we have something that isn't as good a fit, so we actually prefer hydrogen, but we want to keep that in mind as we go forward, because maybe in some cases the accreted matter was mainly helium, and maybe that's what we have now.
Okay, I don't see any additional questions from the audience. Maybe the last very naive question: why cannot we measure the spectral lines?
That's actually related to what I was just mentioning, that the lightest element present floats to the top. Well, the thing is that if you've got 1,000,000 degrees Kelvin on the surface and you've got hydrogen, well, it's ionized.
No, the atomic lines.
Yeah, that's what I mean.
But so the atomic lines should be basically like Lyman lines. They should be fine, no?
Not if the hydrogen is fully ionized. Then you have no lines.
Oh, fully ionized, I see.
Yeah, so it seems very likely that these would be fully ionized. Now, you'd also, of course, if you have something non-magnetic, you'd want to look to even lower energies than NICER has. One of the features that we use, or the absence of which we use to argue that at least the magnetic field isn't in a certain range, is that if it were, you would expect to see at least cyclotron lines. But as far as the atomic lines, yeah, the atomic lines, nothing has been seen, at least with any confidence, in any spectrum of any neutron star, especially isolated ones. And it's thought because that this is fully ionized.
I see. So in principle, even if there is a little bit of, let's say, in the slightly above the surface will be slightly lower temperature, and there will be some hydrogen, the fraction of that will be so tiny, essentially, that it will be invisible.
Yeah, that's right. Now, people have tried in the past. They've argued that if you have an accreting neutron star, maybe one that undergoes a thermonuclear X-ray burst, right, the matter from the companion star is not pure hydrogen at all. It'll have elements heavy enough that it should be able to have lines. Mm-hmm. Of course, this is ongoing, and you're typically having still mostly hydrogen at the top. There were even some hopes of detections, but there hasn't been a confirmation of that. So still no atomic lines. If we got them, if we got atomic lines, then just like with normal stars, we would have an enormous amount of new information about neutron stars.
Exactly. Okay, another question from Wasif Hussain. Go ahead. You want me to read the question? The question is in the chat, actually. So what is the constraint put by gravitational wave constrained by tidal deformability?
Yes, when 3 years ago, GW 170817, these were 2 neutron stars that spiraled into each other. The issue is that when you think about the gravitational waves caused by the orbit, when you have stars separated by many times their radius, they act like point masses. So whether it's two neutron stars or somehow two black holes of the same mass doesn't matter. But as they get closer, there's a tidal deformation because of the mutual gravity. The deformation takes energy. The only source of the energy is from the orbit. And this means it speeds up the in-spiral compared to what it would be if they were, say, two black holes. But this is something that plays a major role only near the end of the in-spiral at higher frequencies where LIGO and Virgo are not very sensitive. As a result, what was reported was only really an upper limit on the tidal deformability rather than a measurement. And that's plenty to accommodate, say, a 13-kilometer star.
Okay, I think there are no more questions, so I guess we will be wrapping this up. I would like to use this opportunity to thank you again for a very nice presentation, taking time to answer all these questions. Most of them were naive, perhaps, but it was very interesting. And I see clapping showing on the screen, so I'll
thank you.
Doing that, and thank you for your presentation.
Thank you for the excellent questions, not at all naive. This is exactly a reason to give presentations so that we can think about these things in more depth.
Right. I definitely learned a lot today, so thank you.